let me take a few minutes to talk about the force aspects when we're dealing with a system of objects. Let's say we have two blocks, M1 and then mass 2, and we're applying a force on M1 like so. And we want to look at the acceleration. We want to look at the acceleration of the blocks. We want to look at, that's what we want to look at. And so for a typical force problem, what I would tell my kids is, first thing you do is a free body diagram. So this is a free body diagram for M1. We've got the force of gravity for M1, normal. We have our pushing force. We also have a force from M2 pushing back on M1 that points in the opposite direction. So this is from the force of 2 onto 1. Great. If I looked at my forces on M2, we have gravity, we have normal, and we have the force from M1 pushing on M2. This force is not pushing M2. This force is pushing M1. And so we have a force from M1 pushing onto M2. Now, these two forces, Newton's third law, these two forces have the same magnitude, just opposite directions. So these two forces are actually equal. So I'm going to call these forces Fn. It's an internal force. Fn. So now I want to determine the acceleration of each block. And so the and there's no friction, by the way, if you haven't picked up on that. And so the acceleration here for block 1 is going to be my pushing force minus Fn is equal to M1 acceleration 1. My acceleration here is going to be Fn is going to be equal to M2 acceleration 2. Now, since M1 is pushing M2, however fast M1 is moving, M2 is also moving. So the acceleration of M1 is going to be the same as the acceleration of M2 because they are a system. And so with this in mind, I know this is simply M1A and this is simply M2A. So what I'm going to do is I'm going to take M2A and I'm going to substitute it in for, since that's my Fn, I'm going to substitute in for that Fn term, and what I end up with is F minus M2A is equal to M1A, and then ultimately what I get from that is F is equal to M1 plus M2 times A. And I can, and of course then I can solve for acceleration for the system for each individual block since it's the same value, and this works perfectly great on this type of problem. One thing to notice is that this internal force does not affect my acceleration. The only thing that affects my acceleration, because acceleration is F net over m, the only thing that affects my acceleration is the mass of the system and the net external force. This is what I had mentioned earlier in my introduction. Internal forces don't affect the motion of a system. That's an internal force, and that does not affect my motion. So, fantastic. Solved the problem. I want to look at it from a different aspect. Okay, same problem. Two blocks, same identical situation. I'm just going to analyze it from a different different way, not a different aspect, a different way. Again, let's recognize that the acceleration for block 1 is the same as the acceleration for block 2, which is the same as the acceleration of the system, which is the same as the acceleration of the center of mass of the system. All of these values are the same. And this is what you have to be able to recognize, because you might be asked for the acceleration for the center of mass, or block 1, or block 2, and you have to recognize that they're all the same. And so I just simply call this A. We know the acceleration of the system is the net external force divided by the mass of the system. With that, my net external force, since there is no friction, is just F. The mass of the system is M1 plus M2. That's exactly the answer we got before by doing 2 free body diagrams, solving for multiple equations. Boom, we get it right then and there. Quite a bit more straightforward, I would say. Now, we can take a look at the individual, that force between block 1 and block 2, and figure that out. A lot of times that's a question. And so if I want to look at the force on M1, and I'm not talking about this F. Remember, if you go back a few minutes, the net force on M1 is this force minus the back force. And so I know my force on 1 is simply going to be the mass of block 1 times its acceleration. The acceleration is this term right here. So my force on 1 is simply M1. My force on M1 is some fraction of my overall force. That's what this term is. It could be half. It depends upon what the two masses are. Similarly, we can determine that the force on block 2, which is M2A, is just going to be M2 over M1 plus M2F. And it's almost like, and the way that I like to think of it is, this overall force is going to be broken up. Some of that force is going to be on M1, some of that force has to go on M2, so that both blocks have the same acceleration, and that's what we're doing here. And this is not an uncommon multiple choice question. I just ratio out the masses, and that's the idea here. Recognize that the F is all external. One question. We saw this on the free body diagram. I said the acceleration of the system is the net external force. Fg and normal force are external forces. Why don't they matter? In other words, if the acceleration is due on only the external forces, gravity and normal force are external, I don't have those factored into my acceleration term. And the kind of the question is why? Well, the answer is Fg and normal force don't affect motion. They are perpendicular forces. And perpendicular forces, these would be a centripetal force. And perpendicular forces don't affect motion. Or don't affect linear acceleration or tangential acceleration, because you have the radial and tangential. So I'm going to put parallel acceleration. Perpendicular forces do not affect parallel acceleration. Now this all assumes that there's no friction with this. If there's friction on those blocks, that's going to be an external force. And if there's friction on those blocks, I got to factor that in. Let me do that right here real quick. So let's say we have a coefficient of friction, mu, between those two blocks. The acceleration is my net external force. So let me just kind of block off this part. The acceleration is going to be my net external force, which is my pushing force, minus the force of friction, which is mu Fn, over the mass of the system. Now, mu Fn, the normal force, is my total gravity of the two blocks. And so this is going to be force minus m1 plus m2 g over m1 plus m2. And so we can factor in if there's friction involved relatively easily. I'm only looking at the external forces that affect the acceleration of the center of mass of the system. Real quick, these two terms do not cancel out. Don't do that. Don't let your kids do that. Let's look at another situation. Now, let's focus on the rope for just a second. Let's say this dot is my rope. That rope is going to be experiencing two forces. It's going to be experiencing a force this direction by a force by block 2, and it's going to feel a force in this direction by F1. The net force on the rope is then going to be, the net force on rope is going to be the mass of the rope times its acceleration. Now you've probably picked up that the acceleration of the rope is going to be the same as the acceleration of block 2, the same as acceleration of block 1, which is acceleration of the system, which is acceleration of the center of mass. I said that really fast. I hope you understood. All my accelerations are the same. Yes. If the mass of the rope is 0, and a lot of times that's stated in the problem by saying the rope is light. We might even say it's massless. Now, there's no such thing as a massless rope, but the mass is so low it's not going to affect the overall mass of the system. If the mass of the rope is 0, the net force on the rope is 0. We have no net force on the 0, which means the force by F1 is going to be equal to the force by mass 2. What this means, and this is an important thing to recognize, what this means is that tension is the same throughout the entire rope. And so I'm going to write it up here because I'm running out of room. Tension, same through rope. So I described it before that when we apply a singular force to a couple of blocks and pushing it, part of that force goes into pushing block 1, part of that force goes into pushing block 2. The same thing applies here. Part of this force is going to go into pulling block 1. Part of this force is going to go into pulling the rope. Part of the force is going into pulling block 2. However, if the rope is light or massless, this force we don't have to pull the rope. This force is going to be split between M1 and M2. Again, our acceleration is going to be the net external force, which is F over M1 plus M2. If the rope did have mass, these two forces are internal. All we would do is add in the mass of the rope as part of our system. We only still have one external force. And so this is not an unusual question. They begin with the saying, here's our situation, a massless rope, get the acceleration, you do the experiment in class, you get a less acceleration. Why? Because the rope has mass, we add to the mass of our overall system. Let's look at another type of problem that we run into with a system that's a very common problem, and it looks a little bit like this. So we have a mass on a tabletop attached by a light rope to a mass that's hanging over a pulley. And all a pulley does is it redirects the direction of the force. It changes the direction of the applied force. Now, in this particular pulley, we're going to say it's ideal. When we talk about an ideal pulley, that means it's massless. The pulley itself has no mass. It also means that there's no friction, and we always pretty much assume this with problems. There's no friction with the pulley spinning. It spins easily. And a lot of times that's, it's talked about a frictionless axle. But when we talk about an ideal pulley, what that means is it has no mass, kind of like the rope. Of course it has mass, but the mass of the pulley is so small, it's much smaller than everything else, so nothing really goes into, nothing is affected by that. In rotational motion, we do talk about the effects of a pulley when it does have mass. So, let's look at the acceleration of the system, and as a reminder, the acceleration of the system is going to be the same as the acceleration of mass 1, which is the same as the acceleration of mass 2, which is the same as the acceleration of the center mass. So a lot of times what I'd like to do, I would give the kids a problem maybe like this, and I'll ask for the acceleration of mass 1. On another similar problem, I might ask for the acceleration of mass 2. I might ask for the acceleration of the center of mass. I try and change up what I'm asking for, even though they're all the same thing. The acceleration of the system is the net external force divided by the total mass of the system. I like to think of this force is we have to account for all the forces that are affecting the motion of this system. And so really the only force affecting the motion is gravity pulling M2 down. There's gravity pulling M1 down, but it's not affecting the motion of the system. And so in this particular case, what we end up with is M2G over M1 plus M2. Now, this assumes that M1 is on a frictionless surface. Okay, what if it's not? If mu is not 0, it's on a rough surface, as problems like to say, we then have a frictional force that's affecting the motion of the system. It wants to slow it down. Gravity wants to speed it up. The friction force wants to slow it down. And so when we look at the acceleration of our system, when friction is present on the tabletop, we still have the force of gravity on M2 acting as in a positive manner, speeding it up. But we have frictional force wanting to slow it down over M1 plus M2. And so, of course, this becomes M2G minus mu, the normal force on 1, which is M1G. Okay. So in this situation, I've defined the force of gravity going down, since that's kind of driving the direction, the motion of our system. I'm defining this as a positive direction, which is why I don't have the negative sign here. I have a positive sign. Since the frictional force is resisting, that's why I have the negative sign. Want one more situation to look at with forces on the system. Okay, one more example, the last example I want to do, which also involves a pulley. By the way, whenever we run into a problem with a couple of masses attached and there's a pulley involved, that's referred to as an Atwood's machine. Obviously named by some guy named Atwood. And so if you hear that term, you need to be thinking about pulleys attached with, or masses attached with a string. There's a pulley involved, that type of thing. And we're still dealing with an ideal pulley. Okay, I'm not gonna change it up until we talk about rotational motion. And so let's say we have a pulley hanging from the ceiling. We have a mast hanging by one string on it. The string goes over the pulley. We have mast 1, and that's our situation. We are holding the blocks at rest. We let it go. This block falls, which of course this block is going to rise. The one thing to keep in mind, this block is pulling on the string down. So there's a tension force on the string pulling down. Well, the pulley is pulling up on the string. The string is massless. These two tension forces are the same. And same thing over here. There's tension in the string, but the tension in these two parts of the string are the same. T throughout, the tension throughout is the same. Because the rope is massless, and the pulley is also massless. If the pulley has mass, these two tensions are not the same. Talk about that a little bit on a qualitative point of view when with the rotational motion stuff. Again, the acceleration of mass 1, the acceleration of mass 2, the acceleration of the center of mass, the acceleration of the system, all the same question. We want to know what's the acceleration. The acceleration is the net external force, the net forces over the mass of the system. The gravitational force on M2 is going to cause the system to accelerate downward. So that's a positive force. The gravitational force on M1 wants to slow it down. It acts a little bit like friction. And so that's going to slow down, or decrease, I should say, our acceleration. So here's a good example where I'm switching up my coordinate system. I'm calling this positive. I'm calling up positive. And we can do that because even if I did it by two independent free body diagrams, I could redefine the coordinate system between the two however I want. This allows me some level of consistency divided by the mass of the system. So very similar problem to what was before, except these masses are vertical. Looked at a bunch of different examples with forces associated with systems. Not that hard. On all of these problems, you could have analyzed it through two separate, or three if you have three bodies, by individual three-body diagrams, summing the forces, just like what I started this video out by doing. Or you can take what I call the systems approach, and it's nothing spectacular, and look at it from our net forces over our total mass. I think this is 10 times easier, if not more easier. So that's Unit 6A. Hope it was some help. Good luck.